Hi, welcome to our Explainable AI course. We'll be looking at theory, application, and research within Explainable AI. In this particular lecture, let's see how to apply SHAP, which is Shapley Additive Explanations for images. So SHAP is by far the most commonly used and most popular technique for within Explainable AI, and let's see how to do that. So in this particular example that we'll be using to explain SHAP for images, we are using ImageNet 50. So there are 50 training images per class and there are 1,000 classes. And the classes within ImageNet belong to many different categories like animals, objects, food items, tools, clothing items, etc. I'll be displaying some of the sample images for you to see. And the neural network, the convolutional neural network that we'll be using in our example would be ResNet 50. And this is the architecture of the ResNet, which I just wanted to show for you to see rather than for you to look and understand. That's not the most relevant thing that you should take away from this lecture. We will see how we apply a pre-trained ResNet 50, which is trained on ImageNet 50 model, and how that can be used for explaining the predictions made by this convolutional neural network model. So the predictions are one among the classes within ImageNet 50, and we will see using SHAP how or why the neural network made this prediction, which pixels within the image contributed towards making this prediction. So our workflow would be as follows. So we load pre-trained ResNet 50, which is trained on ImageNet 50. We will do a little bit of normalization of the images, or rather, we will ensure that the pixel values, the range of pixel values within the image is something that we want. And we will load Shapley explainer for the image. And after that, we'll analyze the features or pixels within the image that contributed to a certain classification. So with that, let's go into the Google Colab coding. I'll be, of course, sharing the Colab notebook with all of you. So this is the Colab notebook that we'll be using. I have already put all the pieces of code here. Most of the code I borrowed from the SHAP's website. And the example that I'm picking here is something that is simple. I don't want to take a complex example like maybe explaining why a particular brain X-ray had tumor or not. I did not want to take such examples because my point is not to show the utility of SHAP. I guess that is more than understood. More, it's very well understood. But I think what I want to show here is how to practically implement SHAP given a set of images and given a convolutional neural network that can make some predictions on this image. So first we install the libraries. We will want SHAP and TensorFlow because from TensorFlow we'll be importing the ResNet 50, and from SHAP we'll be using the SHAP explainer. So I have already run the code, but I'll run once again along with you. So first let us import the libraries. So JSON is needed for getting the image from AWS. And so the image information is in the form of a JSON file. And SHAP is the one which contains the Shapley explainer, NumPy for various tasks, and we have matplotlib. So this is done. Now let us load the dataset. So here we are using ResNet 50. The weights are corresponding to the ImageNet dataset, and so that's the model. And the dataset that we are taking is shap.datasets.imagenet 50. And we are loading X, which are the images, and Y are the labels. And we'll see what are the labels in a moment. So the reason why I'm scaling the images in the next step, so rather than normalize, I would like to call this as scaling maybe. What we're doing here is if you directly try to display these images. So let's say I take this and plt.imshow of some image of index 20, it would look something like this. So this is not good. We would rather have, and I think the values of the pixels ranging the range of values of pixels in X of 20. I just want to see how it looks like within the matrix. 29, 169. So this is how it looks like. So this is not the kind of image that we want to display. So let us scale it and let's display a sample image. So here what we are doing is we are scaling the range from 0 to 255. And if we plot the same image, it will hopefully look much better. So this is the image. So X of 20, this is also X of 20. So this image of these food items is what is being displayed here. So this is why we scale the image. And using this PLT ImShow, you can also look at some of the other sample images. I have no idea what all ranges of images are there because I have not plotted so many of them. But you can plot and see there are people, there are objects, there are animals, tree. So there are many different types of images that we can find within the ImageNet dataset. And these images, the same image can be categorized into different classes. So for example, I think one of the previous images that we plotted, or I think it was, so we saw like a woman. Okay, this one, the label of this can be burger. It can be food item, like food. It can be bun, it can be patty. There are so many labels that we can associate with this image. And in fact, when we make a prediction, we will see the initial few predictions, initial few classes in which the image belongs. And when we print the shape, it's like there are 50 images. It's like RGB 224 by 224 pixel, and that is the shape of X. X is the set of images, and Y are the labels. Now let's look at the ImageNet class names. We are so first, this is where all the class index is there, and we can print the unique values. So let's look at the class names, and let's see whether the class names are indeed 1000. So here we can print the number of ImageNet classes as len of class names. Class names is this variable which contains all the class names from this JSON file. And so this is why we needed the JSON library. And here we are printing some of the sample class names. You can see that. So indeed, the ImageNet classes, there are 1000 classes, and these are the class names. But for ImageNet 50, there are only 50 images in this list. So if we try to print X of 50, this will not work. I guess there will be an error because the length is only till 49. So 49 is the max that we can show here. Okay, so we are selecting a small sample from the image dataset. Okay, so now we define the SHAP explainer. So let's not look at this for a moment. This is simply pre-processing the input image. So a small function that does the pre-processing. But basically, we define a masker. So what the masker does is it masks out certain portions of the image so that we can focus on. So it's like dividing image into group of pixels, which are the features, and masking will basically mask some of these features. So it will create subsets, which are collection of group of pixels. And then in the Shapley explainer, we can see which group of pixels contributed maximum towards making that image prediction as a fighter jet or passenger airplane or whatever. So that's what the masker does. And here we call the explainer from the SHAP library. And F is this function, this pre-processing function. Masker is what we defined here. And the output names are all the class names which we found here. So all the class names, the range of class names are 1000. But since we are only having 50 images, obviously we won't have all 1000 classes in this X input. So now we are calculating the SHAP values. And initially in this SHAP explainer, we are only running 100 evaluations of the model. So you will see what's the difference between this being 100 versus this being, let's say, 1000. And we are using two images from index 19 to 21. So 99, 20 will be taken. And when you run this, you can see. So this part will take a little bit of time because this is where the SHAP values are being calculated. And if this was instead of 100, if this was 1000, it will take even more time. But this is not too slow. So I will pause my video and I'll come back once this part is finished. I don't think it should take more than 1 or 2 minutes. Okay, so that has finished running. It took only a minute. And now we can plot the SHAP values along with the image. So we'll be overlaying the SHAP values on top of the image. So firstly, let's also see what are these images. So it's like a helicopter and like a food item, but it's predicting this as jellyfish. This is definitely not jellyfish, and this is predicted as spider web. I think this is the worst prediction I have ever seen made by like a convolutional neural network. So, but okay, let's have a look at it. So you can see the SHAP values corresponding to this. So this is being classified as a spider web mostly because of these so positive SHAP values, these red-ish values. So these red pixels, group of pixels, are making it look like a spider web, and here these are the group of pixels making it look like a jellyfish. Let us see. Maybe it's because of my okay, first of all, let's hope that the model is working really nicely. Okay, let's see for this X of 49 how it turns out. It must be a fighter jet, the classification. And this time it should not take that much time as before. Timast must be given. Okay, so I guess we can probably give 2 images. And this is so interesting. Let's see how the prediction is. I'm more bothered, like I'm pretty sure SHAP is doing its thing, but I'm more concerned about the quality of predictions. It's not at all good. Okay, so the execution took around 1 minute. I just want to see here the labels. I guess this Y values must be the labels, right? So if I print Y, what does it show? Are those bunch of labels, or it's a collection of these numbers? I don't know whether these numbers indicate the label themselves, because here we are having these class names. Anyways, we'll come back to that, but let's see. First, let me run this SHAP explainer for these 2 images. The one was a fighter jet. Okay, I think sunglasses. Okay, this is really, really bad. I don't want to use this model at all. It's not helping. Maybe let's see what else to do. I know for a fact that when we use the first couple of images, so instead of this, let's say I do image of index 1 and index 2. 2 is, I think, like a speedboat or something. Yeah, so here I hope the prediction is good. Maybe I can try with 1 and 2. Let's see what's the output here. I think I ran this before. This is also one of the examples that is provided within the SHAP documentation. I hope the prediction is good. And this is not sunglass, right? So let's see. Okay, so for the first index 1 and index 2 images, the predictions are good, I guess. It is a speedboat and this is a crane. I think it's a crane only. Let me check crane. Not this crane bird. Yeah, I guess crane looks like this. So that is correct. Okay, so let's ignore the fact that the model is not predicting really great, but at least let's look at the SHAP, because we are not interested in making a great model in this example. We are more interested in looking at the model prediction. So this image was predicted as crane because of these group of red pixels, and it was these group of blue pixels contributed negatively towards the crane. So these groups of pixels did not contribute towards making this a crane. And here also you can see lifeboat, these group of pixels. Generally over here, these group of pixels are contributing towards it being a lifeboat. And interestingly, you can see here is a classification called fountain. And for fountain, these parts where there is water. So if there is a fountain, there will be like a still body, like a plain body of water, and fountain will be in the middle of it. So here, wherever there is this kind of a water splash, you can see it's contributing positively towards being a fountain. And same for this part of the image. Lifeboat, I thought this might also look like a lifeboat, but surprisingly there is not much contribution. Canoeing, again, yes, there is some red pixel here and blue here. Yeah, I guess this is decent. What we can do after this is, let us, instead of 100 evaluations of SHAP, let's do 500. So it will be much slower. So the previous one took 1 minute. This might take 5 minutes. I don't know. Let's run this. I'll anyway pause the image after starting to run this, and I'll come back I'll pause the video and I'll come back once the running is finished. And hopefully the explanation might be a little bit more more distinct. And here we are using a different masker. If you observe, we are using this blur 128,128. In this case, we were using this mask. So I don't want to go into the details of the types of maskers that we can use for masking portions of the image, masking out partitions within the input image, but just notice the difference, and you can play around with it. There are I guess there are different options, so you can play around with this. But my goal is to just see, for the later purpose, when we are working on an actual research problem statement with image kind of data, what kind of explanations can we expect to produce out of that? And you can see that these are the kind of explanations. So if you are a physician and you are looking at some eye disease, and you have some scan image of the eye, and you want to predict the onset of some disease, and you have an convolutional neural network model which classifies a certain image as there is potential for disease, you just want to know which pixels contributed towards that classification. So that is the area, or that is the application where this is most useful. But this is just for demonstrative purposes. I don't want to know which pixels contributed to this being a crane. In real life, it's fairly obvious. I mean, I know why this is a crane. It's not still fairly obvious why CNN, convolutional neural network, made the prediction. Maybe it might be looking at some other group of pixels. So this also helps me convince myself that the CNN is indeed looking at the right group of pixels, which is a good thing, although the accuracy of the CNN is questionable. So I'll pause and come back. As we rightly guessed, it took around 5 minutes, 4.5 minutes. I should not probably say that the model is wrong, because I don't know what are the possible labels. So previously we saw that hat, right? And it was getting classified as like that cap. It was getting classified as sunglasses. I'm not sure if that cap is one of the categories within these class names. What if it's not part of the class name? Then we don't know. So let's not conclude that the model is bad. Maybe it's just that the class name is not there. But anyways, this 500 iterations have been finished, and let's see the SHAP image plot. This should not take too much time. Okay, so now this time you can see that it's much more, the size of these group of pixels are much smaller. And here you are predicting again which pixels are contributing this towards crane and which are negatively contributing. And in speedboat, so previously, let's see if we can do a side-by-side comparison. Probably not. But here you can see that, or rather I'll take a screenshot and then open that so that we can look at it side by side. This is the speedboat from the new 500 iterations. And so this is the new one with 500 iterations. This is the previous one with 100 iterations. You can clearly see that the SHAP interpretations are slightly different, but of course the group of red pixels are still concentrated somewhere around where the speedboat is. But in this case, you can see the accuracy is much better for SHAP. I am pretty sure that is also the case for fountain. So let's have a look at fountain. So here you can see that these are the group of pixels contributing, but the confidence that this is fountain is much less. So you can see that the intensity of the color, the blue or reddish color, it's very low. Here on the other hand, the intensity was still there, comparable. It was still comparable to this. Here there is a little bit of lifeboat color, little bit. I don't know if you can see it when I'm sharing my screen, but it's still there. And American egret, there are these pixels contributing. Is this I don't know if this is like this is the I don't know exactly what's the difference between crane and American egret, but whatever, does not matter. And but ideally what we want to do is, if we are creating a Shapley additive explanation for images, and if the image is complex, like in the sense that if we are trying to predict the onset of a tumor or onset of some kind of disease within the eye or brain or chest, whatever, if it's a healthcare data set, then we want to run more iterations of SHAP, because getting a huge chunk of pixel like this is not very helpful. We want something more very accurate, as well as, I would say, something that can focus on smaller group of pixels. So ideally, we may want to run this instead of 500. We may want to run this for 5,000 and see how much more smaller you can get and how much more accurate you can get. So when we are running SHAP for an actual application, we will not be running like this for such a small number of evaluations. We might run for more. But overall, this is good enough to demonstrate you how SHAP works for images. And I hope that gave you a fairly good idea. I invite you to try this out on a set of images yourself. Maybe you can change the neural network, and you may use a different set of images instead of these and see how SHAP works. But basically, I'll share the Colab link with you. Just take a copy and run it for yourself and see what all things you can observe. It'll be a very, very good experience. So that's all for today's lecture. We'll meet again in the next lecture. Until then, bye and thank you so much.